Welcome to Chapter 7, Part 5, Screencast for Covalent Bonds and Molecular Structure. Suppose we consider the sulfate ion as an example of a substance to do a Lewis dot structure for. Well, sulfur has 6 valence electrons, oxygen also has 6, but there's 4 oxygens, so that's a total of 24 from the oxygen. And then there's a -2 charge, which means 2 further electrons, so 32 valence electrons to put around the sulfur in the center and 4 oxygens around it. 2, 4, 6, 8 for bonds, and then we start filling in electrons around the oxygens to make octets and count carefully, and eventually we get to 32. And that actually looks pretty decent. We have an octet around sulfur, an octet around each of the oxygens. The whole thing overall has a -2 charge, and this certainly seems like a plausible Lewis dot structure for the sulfate ion. And of course, we can represent it instead of as the electron pairs for bonds as lines for bonds. So this looks reasonable. But is there anything else we could do for a Lewis dot structure? And if you note that sulfur is an atom in the third shell or third row of the periodic table, it can actually expand its octet. And so let's look at that again. The electrons that are lone pairs on oxygen here could in fact go in between the two atoms, the sulfur and the oxygen, as a double bond. We didn't change the number of electrons, and now we have 10 electrons around sulfur instead of 8, but we still have octets around oxygen. And in fact, that's a doable thing because, like we said, sulfur can have an expanded octet. And of course, the double bond could have been to a different oxygen atom, or that one, or that one. So we have resonance possibilities, and we have multiple places that we could have a double bond. Now, we could also have 2 double bonds, so we'll go back again a minute, and note that here where there's a lone pair and a single bond, we could in fact have that lone pair go in between the oxygen and the sulfur and have a second double bond, so we could have 2 double bonds to the sulfur atom from 1 oxygen here and 1 there, and of course those could happen in different places as well. Now, how are we going to determine which of these substances, or which of these Lewis dot structures I should say, is going to be the best way to describe the sulfate ion? Well, and in fact we could have more double bonds. Well, how do we best represent the sulfate ion? All of the possible resonance structures in a sense are equally good representations because they all meet our rules. They fulfill octet, or they go past an octet when they're allowed to. And so it seems like they could all be reasonably equal contributors to our resonance hybrid. But
no, that's not going to do it.
It turns out that there is a way to distinguish between possible structures and to predict the structure that would maybe best approximate the molecule's actual electronic structure. And to do this, we introduce a concept called formal charge. Now, formal charge is defined as the number of valence electrons in a free atom minus the number of bonded electrons in a free atom. And we do a formal charge for each atom in a given substance. But here's another way to look at it. It's the number of valence electrons minus valence electrons in the free atom minus half of the bonding electrons and all of the non-bonding electrons. And so essentially what we're doing is we're comparing how many valence electrons the atom normally has with how many valence electrons it has in a compound, taking into account the fact that any electrons that are lone pairs or non-bonding really go with that atom. And the electrons that are bonding electrons, we could essentially say half go with one atom and half go with the other atom that's being bonded. So what we find is that once we've introduced this idea of formal charge, Structures that have a smaller formal charge in general on their atoms are lower energy and more stable, and structures that have a negative formal charge on the electronegative elements in their within them are more stable as well, if there has to be a negative charge, that is.
I don't understand.
Okay, well, let's see if we can make you understand. So let's apply this to sulfate, which is what we started this screencast with. And here was our first structure where we have only single bonds. And essentially what we're doing is we are saying for a given substance, we're going to calculate the formal charge on each atom within this species. So for sulfur, sulfur normally has 6 valence electrons, and right now it has 8 electrons around it, but we're going to essentially share the electrons where half of them are associated with sulfur and half are associated with oxygen. So of those 8 electrons, we're going to subtract half of them, which is 4, and so what we would say is that sulfur has a formal charge of +2. And one way to look at this kind of visually would be to say sulfur normally has 6 valence electrons, but what we're doing is, since these electrons are being shared, we're saying that the electrons that are circled, if you will, in red, we're splitting up the bond pairs and saying one goes to sulfur, one goes to oxygen, one goes to sulfur, one goes to oxygen. And so sulfur really has half of the 8 electrons around it, or 4, that are really associated with it. So originally it had 6, now it has 4. The difference is +2, that's its formal charge. And if we do the same thing for, let's say, oxygen, then it normally has 6 valence electrons. It has around it at this point, the number that have to be subtracted would be 1, 2, 3, 4, 5, 6 that are lone pair electrons that are only part of oxygen, and then one of the 2 electrons in this bond, so it actually gets all of, and why did that not work? Let's try again with the pen, and let's give it a color. So let's do green this time. So these electrons, 1 electron here, these and these, so that's 7 electrons that are associated with the oxygen, so it has a formal charge of -1. And if we do the same thing with other oxygens, we will find they have the exact same formal charge. So what we would say here is oxygen has a formal charge of -1 on each of the oxygen atoms, and sulfur is +2. Now, note that the +2 formal charge for sulfur plus 4 times -1 for the oxygen adds up to the total charge for the ion, which is better because formal charges are kind of like charges that these atoms would have if we shared the electrons equally and then just said, hey, what's their charge if they were now an ion? Okay, well, let's look at one of our other examples where we have a double bond for the oxygen-sulfur bond here. And if we do the formal charge on this oxygen, it's like we had before. We have a six electrons normally around the oxygen, 7 now around the oxygen, so 6 minus 7 gives us -1. That's going to be the same here, and that's going to be the same here. But on this one, we have, and again, we'll split the electrons in half when they're shared. So for this oxygen, it would normally have 6 electrons. It actually has 6 electrons around it, so that's going to have a formal charge of 0. So this is going to be 0. And then for the sulfur, let's do that in a different color. We have half of the bond, half of the bond, half of the bond, and half of the bond. So sulfur normally has 6 electrons. Now it has 1, 2, 3, 4, 5. So that gives it a formal charge of +1. Now that's closer to 0, so this is actually going to be better in terms of formal charge than the previous structures. And now let's try the double bonded one. And again, let's do the sort of pen thing. So for this guy, we count all the lone pairs and half of the bond pairs. So oxygen would normally have 6 electrons. Now it has 7, formal charge of -1. Same for this guy, formal charge of -1. And for this one, it would have normally 6 electrons, now has 6 electrons, formal charge of 0. And let's change colors to do sulfur. So sulfur has half of the bond electrons here, half of the bond electrons there, half and half. And so in this case for the sulfur, it normally has 6 electrons, and it has 1, 2, 3, 4, 5, 6. 6 electrons now, so formal charge of 0. And if we put all of those in, -1, 0, -1, 0, and 0 for formal charges, and that's as good as we're going to do if we are dealing with something that overall has a charge of -2. And also note that the -1 formal charge, the not 0 formal charge, is on oxygen, which is more electronegative than sulfur. So if anything's going to be slightly negatively charged, that seems pretty reasonable. It's more likely to be oxygen than sulfur. So this is the best structure according to formal charge. And once again, we're doing the charge for each formal charge for each atom in the substance, and the lower the better. And if anything has to be charged, then it's better to have negative charge on the more electronegative elements. And one could try this for the one with 3 double bonds, and you might want to try this yourself, but note that what's going to happen is now you get one more oxygen atom to have 0 formal charge, but at the cost of sulfur having a -1 formal charge, and that's less likely than oxygen having a -1 formal charge because sulfur is not as electronegative as oxygen.